All right, everyone, let's get started. So I hope you guys can hear me and see my slides also. Can someone confirm that?
Yes, sir.
You can hear me, right?
Yes, sir. Yes.
Okay, good. Yeah. So I guess we have been doing fluid mechanics in the last 3-4 weeks, and we have looked at problems from fluid kinematics, statics, and a bunch of problems from continuity as well. So we'll continue with our fluid mechanics topics and let's start with this one. So this came in GATE 2020 set 1 and is question number 50. So I suppose a 2 marks question. And the question is air discharges steadily through a horizontal nozzle and impinges on a stationary vertical plate as shown in figure. The inlet and the outlet areas of the nozzle are 0.1 meter square and 0.02 meter square respectively. The density of the fluid is given. So it's air, I suppose, yeah. So 1.2 kg per meter cube. And if the inlet gauge pressure of air is 0.36 kilopascal, the gauge pressure at point O on the plate is, so point O is just at the start of the plate in kilopascal. So I guess we have solved problems like these. And does anybody want to take a crack at it and tell me how we should solve this? I guess there are a very small number of people today, so let's try to keep this interactive. So anyone wants to tell me how we can solve this?
Bernoulli's principle.
Yeah, perfect. Yeah,
Yes, sir.
you're,
One
yeah,
principle.
yeah. Both of you are right. So we have to apply the Bernoulli's principle, and I guess once you do that, it's pretty straightforward. But again, we have to take care of the units here. So in the end, you have to convert it into kilopascal if you are trying to solve it in pascals. And yeah, so this is the Bernoulli principle again, and these are the three assumptions. As I always say, keep these assumptions in mind. So let's see if these assumptions apply to our case. Steady flow, so it does say steady. And since the density does not change, well, we can say that this is a constant density fluid, and also there is no information of viscosity given to us. So it makes sense to also consider this as an inviscid flow. So all these three situation applied in our case. So it's pretty straightforward to apply the Bernoulli's principle now. So I guess I'll just draw it here. So let's say that this is our point 1 and this is our point 2, and finally this is our point 3 which passes through O. And so all these three are at the same datum, same distance from the datum. So when you apply the Bernoulli, you can simply just say that Z1 is equal to Z2 is equal to Z3 and neglect the potential head after this in the Bernoulli's equation. So you'll only be left with P over rho g plus V square over 2g being constant. Now, what is not given to us is the velocity. So for that, you need to invoke the continuity equation first. And so let's say that velocity here is v1 and velocity at the exit is v2. Then invoking the continuity equation, we can simply say that a1 v1 is equal to a2 v2. So this comes from continuity in one dimension. And a1 is given to you. So this is a1, let's say. A1 is zero point 0.1 meter square and A2 is 0.02 meter square. So then this becomes zero point 0.1 into V1 is equal to 0.02 into V2, and you can just write 10 V1 is equal to 2 V2, or V2 is equal to 5 V1. Right, so now we know the relationship between V1 and V2, and we also know the pressures at the inlet and the outlet. So pressure at the outlet is given as atmospheric pressure, whereas pressure at inlet is 0.365. So we can apply the Bernoulli's at 1, 2, and we'll get P1 over rho g plus V1 square over 2g is equal to P2 over rho g plus V2 square over 2g. Now, if you notice that P1 or P inlet given to us is in gauge pressure, and P atmospheric is just atmospheric pressure. So in terms of gauge pressure, this is zero. Okay, so any gauge pressure is equal to the total pressure minus the atmospheric pressure. So basically P2 will become zero since this is just atmospheric pressure, and then we can neglect this also, and we can cancel out g's from all the denominators, and then find V1. So this P1 will be 0.36 into 10 raised to the power 3 in pascals. Density given to us is 1.2. Let's keep V1 as V1 for the time being. So this is V1 square by 2 is equal to, now instead of V2 you can substitute 5 V1. So this will become 25 V1 square over 2. So then I guess from here you can calculate V1. So this goes to the right hand side. This will become 24 V1 square by 2, or I can just write 12 V1 square. And this you can say is 3.6 into 10 is to the power 2 over 1.2. So that will be, yeah, that will be 3.
300.
Yeah, 300. You're right. So again we can cancel 12 and 3 and say that V1 square is equal to 100 over 4.
V1 equal to 5 meter per second.
Yeah, perfect. So V1 turns out to be 5 meters per second for us. And then you can substitute this V1 here and get V2 to be 25 meter per second. Now in the question they are asking us to calculate the pressure at this point, and it's pretty straightforward because we know the pressure here, we know the velocity here and here. So velocity here will go to zero because it will uh, hit this flat plate, and then there will be no flow across the plate. So again you can apply the Bernoulli between 2 and 3 and just write that. So P2 is already 0 for us. So this will be like V2 square over 2G is equal to P3 or PO. I'll just write PO over rho G plus V3 V3 square over 2G. Now we just said that V3 will be 0 for us. So then you just need to calculate PO, which will be equal to, so G and G again cancels out. This will be equal to rho times V2 square over 2. Yeah, I hope I have not missed anything here. So rho for us is again 1.2. V we just saw was 25. So this is 25 into 25, that is 625 divided by 2. And Yeah, if you solve this, let's see. Can someone tell me?
375.
Can you repeat?
375.
Yeah, so this is 375. But again, okay, let me just write it here. P naught will be 375, but this is in pascals.
Pascal, yeah.
Yeah. So now,
0.375.
yeah,
Would be the
exactly.
KPA.
So you just divide by 1000 and just say that this is 3.375 kilopascal. Yeah. So yeah, I guess the only thing here you need to be careful about is this Pascal to kilopascal conversion at the end. And yeah, the mistakes mostly happen at this point. After doing all this hard work, you can just forget to divide by 1000, and that will be disastrous. So is this clear? I think this is pretty straightforward. If anyone has any questions, please ask.
Excuse me, sir.
Yeah, Ashwin.
Sir, in Bernoulli's equation between 1 and 2,
Yes.
it was 12v square equal to, uh,
Where, Ashwin?
oh, yeah, yeah, sir, got it. Sir.
Oh, okay. This
I
is
missed
clear,
it.
right? Oh, yeah. So I divide by 2 also. So this 24 becomes 12.
Yes, sir, got it.
Okay, fine. Yeah. Okay, then let's move on to the next one quickly. Yeah, this is a good question, and this came in K 2021, and this is again a 2 marks question. So water flows out from a large tank of cross-sectional area AT, that is 1 meter square, and then it flows out through some small orifice which has cross-sectional area A naught, located at y is equal to 0. Now, initially, the water level measured from y is equal to 0 is h equal to 1 meter. The acceleration due to gravity is 9.8 meter per second square. Electing any loss, the time taken by water in tank to reach level of h by 4 is. So here you need to again apply the mass conservation or mass continuity equation. But the only thing is, most of the cases when we have been applying the mass continuity, this term is 0 for us. The dm dt term is 0 for us. But here, let's say there is, again, I think we did some question like this last time also. So here there is some flow rate coming in, mass in, and there is some flow rate going out, mass out. So the difference between that is what is being accumulated here. But if the mass coming in is less and mass going out is more, then we are losing out on mass inside this control volume. Let's say this is a control volume. So inside this control volume, you can either have accumulation of mass or removal of mass, or you can have a case where the flow is non-divergent, and then whatever comes in also goes out. So basically, uh, the mass inside this remains the same. So there are these three cases, and in the third case, when there is no change of mass, this dm dt goes to 0, and you say that mass coming in is equal to mass going out. But in this case, we will have dm dt being equal to non-zero, and that is how you solve for this time it will take to come from h y is equal to h to y is equal to h by 4. So let's try to see this. Yeah, let's say that you have this container. So this is your A naught. This is the reference point, and this is the initial configuration where our container is filled up until the height h. And this is, let's say, some y. So y goes in the top direction. Now let's try to invoke the mass conservation equation, that is mass coming in minus mass going out is equal to rate of change of mass inside this container, or the control volume you can say. So it's easy to see that there is no mass coming in, so this goes to zero basically, and then simply the mass going out is equal to the rate of change of mass inside this container. Right. Now the mass going out, we have I think seen this. So okay, since this is the same fluid, this mass can also be changed to flow rate, but let's keep it at mass for now. So this mass going out will just be rho times the volume, uh, instead of volume, why not we just write rho times area times the velocity at this small orifice, and this area will be a naught. Now the velocity out of this orifice will be, again you can derive this from Bernoulli's. This will be 2gy, where y is whatever is on top of this orifice. So this is the mass going out. Yeah, did someone have any doubt? Okay, I don't think so. So this is there, and then this dm dt, so rate of change of mass inside this control volume, will just be equal to d dt of rho times the area here. So this will be your AT, area of the cross section of the container, times y, or you can just say, you can take this and this out and just say this will be dy dt. Now substituting both of these in this equation number 1, you can now say that rho a t dy dt is equal to rho a naught rho 2 gy, and there is a minus sign somewhere. So this rho and rho gets cancelled out. Now dt you can take on the right side and everything on the left hand side. So then this becomes at over a naught 1 over root 2g, and this becomes dy over root 5. Now we will integrate in order to find the time. So let's say this starts from t is equal to 0, and at t is equal to t1, let's say you reach at h by 4. So this starts from t is equal to 0 to t is equal to t1. dt is equal to, so these are all constants, they can be taken out of the integration, and this is dy over root y starting from h, because at the start when time was 0 this container was filled up until h up, and now at time t1 it will be at h by 4. Okay, so now you can simply integrate. So this dt becomes t1 or t, let's say, and then we will put on the limits at the end. So this is 0 till t1. At over a naught you can just substitute. So at is 1 meter and a naught is 1 centimeter square. So that will be 10 to the power minus 4 meter square. So this is 1 over root 2 times 9.81. And if you integrate 1 over root y, okay, there is a minus here, I think. If you integrate 1 over root y, you will get root y at the top and 1 by 2 at the bottom. and you put on the limits now from h until h by 4, and let's try to see this now. So this will be t1, and this is minus 1 over, or you can just write 10 to the 4 divide by 1, not just 1, let's not write it, 2 into 9.81, and there is a 2 at the top. And if you put on the limit, so this root h by 4, or we can substitute for h equal to 1. So this will be 1 by 4, and if you take it out of the square root, this will be 1 by 2. So this is 1 by 2 minus 1. And then this minus and minus you can absorb, and this will be just 1 by 2, and this gets cancelled by 2. So in the end, you just get 10 to the power 4 over 2 into 9.81 under root. And if someone has solved this, you can tell me the answer to this. Yeah, so if you solve this, you'll get 2257.6 seconds. So this will be your answer to this, 2257.6. So, alright guys, this is clear. I guess this is one of the problems which is on the harder side. So I think this requires some thinking, and then it also requires some time in order to calculate it.
Sir, any other methods are there or only do this method only, sir, for this problem?
Yeah, I am not aware of any other method. Uh, I think this is the only method I know. If they, of course, there might be some other method also. If anyone of you has any other approaches, we can look at that also. But this is like going from first principle, so I guess this is the easiest to understand at least. A little time taking though. Yeah, that is true. Okay, let's move on to the next one then. Yeah, this is also from 2021. So this is a cylindrical jet of water impinges at the center of a flat circular plate and spreads radially outwards, as shown in the figure. The plate is resting on the linear spring with the spring constant, some spring constant is given. And the incoming jet diameter is also given. So this is 1 centimeter. Now, if the spring shows a steady deflection of 1 centimeter upon impingement of the jet, then the velocity of the incoming jet is. Alright, so in order to solve this question, you need to remember this formula. So whenever you have a flat plate and there is a jet which is impinging on it perpendicularly, so let's say this is your flat plate and this is some jet, and the diameter of this jet is, okay, let's say that the cross section of this jet is A. So in that case, this jet will apply some force on this plate, and that force is given by this formula. So here rho is the typical density of your fluid. A is the area of cross section of the jet. This is area of cross section of the jet. and v is the velocity with which the jet is flowing perpendicular to the plate. And this, I guess everyone knows. So this is spring force. Spring force is given by just the uh, product of the spring constant and the deflection in the spring. So basically, this is S is proportional to the deflection, and then this spring constant comes in, and then you have the force, restoring force of the spring given by S is equal to kx. That's all. So these are the two forces at play in this question. And so once you know this, then I guess this is just a matter of doing force balance. And yeah, just try to see this. So as we said that you will have force exerted by the jet on the spring that will be equal to rho times a times v square. And here the velocity v is unknown to us. So v is something we have to find. Diameter of the jet is given as 1 centimeter. So this will lead us to the area of the cross section of the jet, which will be pi by 4 times this 1 centimeter, meaning 10 to the minus 2 meter, or this is 10 to the power minus 4, because pi by 4 d square, and there will be meter square. Density is also given to us as 10 raised to the power 3 kg per meter cube. And for the spring force, let's say S, you just need K and X. The deflection is given as 1 centimeter. So X is given as 1 centimeter and K is given as 1 kilonewton per meter. So again, this kilonewton we can convert into newtons. So this is 10 raised to the power 3 Newton per meter. So S for us is 10 raised to the power 3 into 1 centimeter, which is 10 raised to the power minus 2, 2 meters. Now you just do this force balance where the force applied by the jet onto the plate is equal to the force, restoring force of the spring, and then this just gives you the answer. So rho is 10 to the power 3, area is pi by 4 into 10 to the power minus 4 into v square, that is equal to the spring force, which is 10 to the power 3 into 10 to the power minus 2. So let's please solve this and tell me what the velocity is.
11.3 meter per second.
11.3 meters, is it? Yeah. So I guess this is just trivial calculation. You guys can do it, and then I think the answer will be 11.3 meter per second. So all you need to know is the force exerted by the jet onto the plate and the spring force. That's all right, let's move on to the next one then. Yeah, this is slightly going back. So this is now kinematics again. And yeah, I'll put this question in the screen, and I would like you guys to try this one right now and tell me the answer. This is very easy, and if you have attended the previous classes, you will know how to solve this one. So guys, please try this and write down your choices in the chat, and we'll see how many get it right. And this should not take you more than 3 minutes, so I'll give you 3 minutes to solve this.
Sir, should I apply Euler equation, right, sir?
Yeah, you're right. So you can see these assumptions, and immediately you will know that this is Euler's problem because this is
Then
incompressible
the
frictionless fluid.
option B, sir.
Which option, Vijit?
Option B.
Option B is it? Okay.
D.
Uh, Priyanka, you said D or B?
D. Fourth option.
Okay. Uh, let's see. Uh, Others also put their answer in the chat. Let's see.
Minus rho xi cap plus yj cap. Mine option.
Hmm. One more minute, guys, and then we will try to look at the solution. So did the others try it? Suraj, Vikas, Setu?
Sir, B, sir.
Yeah, okay. B. Okay, so I guess the correct option is B. And so Priyanka, did you do some error in this? Because you just need to do this, I think. Yeah, so you need to apply the Euler's equation. Let's just look at the solution, and then we can see if there are some issues here. So this is our Euler's equation in two dimension now. So okay, this velocity vector is u comma v, and this is capital V, just to not confuse it with the scalar velocity v. So this dv dt, which is the material derivative, will just be equal to, okay, why don't we write it rho times dv dt. So this is our Newton's equation. Rate of change of velocity is equal to rate of change of momentum is equal to force, and this force is just the pressure gradient force, right? And then everything else here is zero, so you will have other forces coming in because of friction, but the viscous forces namely, but because it's a frictionless flow, this goes away. Then you have just this, and then I guess you can write it into component form. So this will be equal to dv dt plus u dot grad u. Why don't we write v dot grad v instead? Yeah, v dot grad v, and this is equal to minus the pressure gradient. Now they are asking us to calculate the expression for pressure gradient vector. So this minus has to be shifted there, and after this I'll just write it into the component forms. So this rho will be there in both the components, minus will come, and for the u direction this will be equal to du dt plus u du dx plus v dv dy, v du dy, sorry, and all of this will be I cap plus, now the j cap terms will come, dv dt plus u dv dx plus v dv dy. Okay, so this is our pressure gradient. Okay, I can just write it here. So this is grad of P. So again, grad of P will be equal to, now since U and V are, okay, let's also write what U and V for us are. Since this velocity vector is given as xi cap minus yj cap, then the U velocity vector becomes x and V velocity becomes minus y. Now it's just a matter of doing the partial differentials again. This is minus rho, and this term immediately goes away because both these u's and v's are not a function of time for us. So this is like a steady flow. And then this u will be, let's substitute u, which is x, and du dx will be equal to 1. Now if you see du dy, u is not a function of y, so this term also goes away. So this is this times the I cap vector plus, now again dv dx, since v is not a function of x, this also goes away. You have v times dv dy where v is minus of y, and dv dy will be equal to minus 1. So then this grad of p becomes minus rho xi cap plus y. Okay, there will be a j cap here. I should not forget the j cap. Yeah, yj cap, and this is the final expression for your pressure gradient vector. So then this matches with yeah, B option, I suppose. So
Sir,
yeah,
hello, sir. Can
yeah,
we
because
use here del P by del S equal to minus rho g, and in place of g we write a, and a calculate and return this.
uh, can you repeat, Vikas? I don't understand actually what you are asking.
Sir, if we hydrostatic law del P by del S equal to minus rho g.
Hydrostatic law is in the in the z direction, right? So I don't know how you use that here.
Yes, sir.
Yeah. So okay, this talks
Sir,
about the flow in 2 dimension. I don't think you should be applying hydrostatic law and using pressure gradients here, because pressure gradient will strictly be given by this formula, grad of P, which is equal to partial P partial x I cap plus partial P partial y j cap.
okay.
Yeah. So Priyanka, this is clear now, or
Yes, sir. It is clear, sir.
okay? Yeah. Okay, then I think we can move on to the next one. Oh yeah, I think yeah, we just solved it here, and correct option is B. So let's move on to the next one. So this is from GATE 2019, and this one just says that cube of 100 side 100 is placed in a bottom of an empty container on one of its faces. The density of the material of the cube is 800 kg per meter cube. Liquid of density 1000 kg per meter cube is now poured into the container. The minimum height to which the liquid needs to be poured into the container for the cube to just lift up is. So, what force balance should we apply here? Anyone?
UNC force, sir.
Yeah, buoyancy force, but that will be equated with what? So buoyancy force acts upwards in order to lift the cube when we pour water, but something is acting downwards, right?
Wait.
Gravity.
Yeah, exactly. Yeah, gravity of it. Yeah. So this is also simple. Basically, what you need to do is do this force balance where W is the weight and equated it to FB, which is the buoyant force. Now weight will simply be given by rho times the volume of the cube times g. So this is Vc, volume of the cube, whereas buoyancy force will be given by, so this is rho of cube, volume of cube times G. This will be given by rho of fluid, and yeah, fluid I suppose is water because this liquid has density 1000 times volume displaced times G again. Now if we do the balance, so this rho of C is given to us as 800. Volume, since this is a cube, we can just take it as cube of its side. So this is 100 mm, which will be equal to 0.1 meter. So this is 0.1 cube times G. Now the density of the fluid is 1000, so this is 10 raised to the power 3. Now the volume displaced will be the area of the cross section, which is again same as the cube. So this is 0.1 into 0.1 times the height up until which uh, this is filled, so that it displaces it lifts the cube basically, and then G comes. So you just need to solve this for H, and yeah, this is fairly straightforward, and I think you can cancel two of these from here, and this will be 80 divided by 10 is power 3, so that is 0.08 meters. And now again, so basically there is a trick in this question again. You should not just put 0.08 here and see the units and then suppose, right? So you multiply it by 1000 and then this becomes 80 mm. That is the correct answer to this problem. Yeah, I think this is easy, so we'll just straightforward move on to the next one. And this is the last problem for today, and okay, this one is again a bit involved problem. Let's go through this. So two immiscible incompressible viscous fluids having same densities but different viscosities are contained between two infinite horizontal parallel plates 2 meter apart as shown below. So they've given this figure. The bottom plate is fixed and the upper plate moves to the right with a constant velocity of 3 meter per second. With the assumption of Newtonian fluid, steady and fully developed laminar flow with zero pressure gradients in all directions, the momentum equation simplifies to this. So they have given us the
Newton's
momentum
law of
equation.
dynamic viscosity. I have to apply that.
What have you applied, Abhijit?
Newton's law of dynamic viscosity.
Yeah, you are right. Yeah. So that will be used here. You are right. And basically, what they are asking us to calculate is the velocity at this interface. Okay. So now let's try to see this. He is right, Abhijit is right. You need to apply the Newton's law of viscosity. But before that, you need to do a bunch of things actually, and that we will do. So this comes from using the whole Navier-Stokes equation and applying all these assumptions. So zero pressure gradient, fully developed flow, laminar flow, and the fluid being Newtonian and steady. So also incompressibility you have to invoke. If you apply all these equations, the whole Navier-Stokes equation just reduces to this simple expression. So d square u by dy square is equal to 0. Now,
Sir, immiscible means
uh, what did you, can you repeat?
two immiscible first point, sir, and two incompressible viscous fluids.
Yeah, what about it?
First, immiscible means
Immiscible means, okay, okay. Immiscible means basically these two fluids will not mix with each other. So if you have, let's say, uh, two fluids which can mix with each other, let's say you have some lemon juice and so concentration of lemon with water, you can mix lemon with water, right? Lemon extract. But if you talk about oil and water, let's say, oil really does not mix with water; it just floats over the surface. So it's something like that. So these two will not mix or are permeable within each other. That's all.
Okay.
Yeah. So okay, let's continue this. So we start with here, and from here you can simply solve this differential equation. So we can integrate it once and say that du dy is equal to some constant a, and then u as a function of y will be a times y plus b, and these a's and b's are your constants or unknowns here. Now for these two fluids, we can have different set of a's and b's depending upon mu1 and mu2. Let's just first write down the other given information to us. So here they have written that the dynamic viscosity of lower fluid mu2 is twice as that of upper fluid mu1. So simply mu2 is 2 times mu1. So we have this, and now let's look at the lower fluid and say that u at y for lower fluid is a2y plus b2. These two constants. And since this bottom plate is at rest, we know that u at y is equal to 0 will be equal to 0. So this naturally leads us to find that b2 is equal to 0, or u as a function of y for the bottom plate of sorry for the bottom fluid will just be equal to a2 times y. Now let's try to see what the velocity of this bottom fluid at the interface will be. So u at y is equal to 1, since at the interface y will be equal to 1, and this will be equal to a2 times 1, or simply a2. So let's call this as 1. We'll be using that. Also, let's try to look at the shear stress at the interface at the interface. So basically at y is equal to 1. So we have seen from Newton's law of viscosity, the shear stress is given by tau is equal to du dy times mu. So for the bottom fluid at y is equal to 1, this tau at y is equal to 1 will simply be mu2, and du dy we can just write as a2. Right, so so this is let's say equation number 2. Now let's try to focus on the upper fluid. Again, we can invoke the no slip condition at the top of this plate, and since this plate is moving with a velocity of 3 meter per second, okay, let's just write the velocity profile for this. So let's say this is a1y plus b1, and at the top, so velocity at y is equal to 2 will be equal to 3 meters per second, and this implies that a1 2 times a1 plus b1 is equal to 3. So now the interesting part comes now. Since at the interface you can only have you can't have two velocities going on. So at this interface you will have the shear stress and the velocity of the upper and the lower fluid being equal to being same. So let's just see the velocity of this upper fluid at the interface, or at y is equal to 1. So that will be equal to a1 plus b1. Also tau at y is equal to 1 will be equal to mu1 times du. Okay, this is not partial, this is, yeah, du dy, and du dy for us is again a1 here, so this is mu1 a1. And since tau, so let's call this 3 and this 4, and we can use from 2 and 4 taus at, so the shear stress at the interface has to be same, and that will mean that mu2 a2 is equal to mu1 a1. And from here we can calculate a2 in terms of, or a1 in terms of a2, let's say. That is better. So a1 is mu2 over mu1 times a2. Yeah, or why don't we just calculate a2 in terms of a1? That is actually better. a2, wait, oh, I guess I just removed everything. I'm sorry guys. Yeah, this is a problem. You'll have to bear with me. I have to write down the whole thing one more time, so I'll go through it quickly. So simply u will become a y plus b, and for the upper fluid, oh sorry, for the lower fluid, we had found that b was equal to 0, so b2 was equal to 0. U was a2y plus b2. So velocity was simply a2 times y, and at the interface that velocity was a2, and also at the interface tau was equal to a2. And for the upper fluid, let's write it here. For the upper fluid, we found that uy was a1y plus b1, and at y is equal to 2, so this was 2a1 plus b1 being equal to 3, because the upper plate is moving with a velocity of 3 meter per second. Also at the interface the velocity was just a1 plus b1, and tau at interface was just a1 times mu. Okay, this should be multiplied with mu, and this will be mu2 and this will be mu1. Now we are saying that at the interface the shear stress is same, so let's call this 1, 2, 3 and 4. So from 2 and 4 we can just write a2 mu2 is equal to a1 mu1, and since mu2 is equal to 2 mu1, so we can write a2 2 mu1 is equal to a1 mu1, and then write a1 is equal to 2a2. Also the velocities at the interface will be equal, so this has to be equated with this, so these two have to be equated now. So basically a1 plus b1 is equal to a2, so that we can write as a1 plus b1 is equal to a2, and a2 or a1 we have just found is equal to 2a2, so 2a2 plus b1 is equal to a2, which means that, oh yeah, and this is also there. Let's say this is 5
A1
a1 plus b1, yeah. So from 5 we know that 2a1 plus b1 is equal to 3. So okay, probably it's better to yeah, we can just do it like this also. So 2a2 minus a2 is a2 plus b1 is equal to 0, or b1 is equal to minus of a2. So here we can substitute this. So 2a1 minus a2 is equal to 3. But we know that a1 is equal to 2a2. So this is 2 times 2a2, just basically 4a2 minus a2 is equal to 3. So from here you can find that 3a2 is equal to 3, or a2 is equal to 1. Now since they are asking us to calculate the velocity at the interface, that will just be equal to simply a2, or you can also say that it is equal to a1 plus b1. So velocity at y is equal to 1, or at the interface will be equal to a2, and that will be equal to 1 meter per second. And I guess that's the solution to this problem. So a little involved problem again, and this might be a bit time taking also.
Yes, sir.
Yeah, but there you can expect at least 5 to 10 marks of or at least 5 to 10 questions which are time taking and which are involved. So the key is to identify those problems and see if they are solvable, or if you have time, sufficient time to solve it. Otherwise skip it and take a look at them at the end, because what happens is sometimes we get so caught up in solving these problems, and we take the problem personally. So you will think that, okay, I have spent 2 minutes, 3 minutes, 4 minutes into this problem, and I'm so close to the solution. So why not just keep on going? And then this becomes a problem, and you'll miss out on the easier problems, which are probably in the later half of the exam.
Yes,
So
sir.
yeah,
And and how to identify
yeah. So
problem?
basically, I don't know. I mean, it depends. I guess this is also where I would say that keep doing test series. You will have this feeling that, okay, I am spending more than sufficient time on this problem, so it's better I skip it. Keep that page with me, so that rough page, so that I can continue from wherever I have left, and revisit this at the end if I have time. So these things will come with practice, and practice in a exam like environment. So basically giving test series. That's why every week I am asking you guys to please try to give test series as soon as your these final semester exams get over, because the amount of preparation, not just preparation of concepts, but the mental preparation you will get from test series, you will not get it anywhere else. Yeah. Okay, but yeah, because
Sir,
yeah,
earlier we solved XCA, right, sir? Maths.
uh, XC. So you are saying this
Maths.
engineering sciences, right?
Yes, sir.
We looked at
We
some
solved
problems,
a.
right? Yeah, yeah.
Yes, sir. Actually, if you can help with some weird topics in that, like, because some topics are, some questions are such that, like, we cannot solve it with direct concepts. Like,
Uh,
if there are set, like, after we complete all this, like, if we
yeah, yeah,
have
yeah, yeah.
some awkward questions from that, like, which we can't solve with direct formulas or something, like,
Mm-hmm. Yeah, I get
just,
it. I get it.
just
There
concepts.
might be some question. Ashwin, can you, if you are trying those XC papers, can you note them down and maybe at the end send it to me, like bunch of questions? Because it won't be possible for me to go through all these XC exams and identify which problem are out of the mechanical syllabus. So if you are solving it one by one, probably if you identify if there are few problems which can be solved in the class, which are, as you say, tricky, we can do that once we wrap this fluid mechanics part up.
Thank you, sir. Yes, sir. I'll see this.
Okay, good. Thanks. Yeah.
Sir,
Yeah.
whole gate question paper is made by the all IITs or a organizing IIT like all IIT Kanpur only.
No, I think it will be made by one, just the organizing IIT, right? And that's what I used to think. I'm not sure, but I think it's so the IIT which conducts this organizes this year's GATE exam will be the one preparing the exam, or I'm not sure, maybe it's different.
Okay, sir.
Yeah, but instead of focusing on that, I would say just focus on doing previous year questions and practicing, and just practicing. That's all.
Okay, sir.
Yeah, yeah.
Sir, one thing I have to ask you that after fluid mechanics, what module will you start?
I will probably go back to this as Ashwin said, we have some XC questions that we would like to look at. I will probably go back to maths or maybe radiation in heat transfer. So that's what I have in mind.
Yeah, heat transfer would be great and math would be great because Fourier series. Yeah,
Yeah,
that
yeah.
would be relatable. Yeah,
Yeah,
thank you,
so
sir.
basically math is what I'm most comfortable in. Heat transfer, okay, maybe radiation I can manage, but other than that, probably I'll go back to math and solve. So the thing is, math is very important also. So I really want you to guys to focus on math and don't miss out on any questions or any topics from maths at least.
Okay, sir.
Yeah, yeah.